We recently talked about how to find numerical approximations for the derivative. This video is going to help us find graphical approximations for the derivative. And the way we're going to do that is to look at pictures of functions, and we're going to analyze various neighborhoods of those functions, specifically to try to find the slopes, the small rates of change of the functions and where they exist across their domain. And then what we'll do is we'll plot those slopes on top of the same picture to see if we can connect them and make a pattern, what will be our approximation sketch for f prime of x. What I will do is use red for my notes and for my slope calculations, and then when I'm finished, I'll use blue to connect the dots and hopefully see an image or just a rough sketch of what we believe that function, that derivative function will be. So let's begin with number one. We have a linear function, and that's defined as simply f of x. And what I want to know is, what is the slope of this line? Now, the slope is constant everywhere across this line. So if I just try to count up here, it looks like I can rise up 2 and maybe run 1, 2, 3. So this slope would be up 2 and over 3, or rise over run of 2/3. So that being the case, my derivative then is going to be just that, y equals 2/3, or f prime of x equals 2/3. And that's going to be this horizontal constant right about there at the line y equals 2/3. So let's label that. I'll use blue to label that f prime. The next picture is a parabola, and it's not quite as easy to see because I have a changing function, essentially. I have a slope on the left right here. This looks like maybe -3 if I'm just kind of estimating down 1, 2, 3, and then over 1. So a slope of approximately -3. On the other side of the parabola, which is symmetrical, I might say that I have a slope of +3. So maybe I draw a little tangent line over here, and if I just approximate that line down 1, 2, 3, and over 1, so approximately -3 would be that slope over here. Oh, I'm sorry, +3. +3 on the right-hand side, and then -3 on the left-hand side. And then notice this. I have actually, right here at the vertex of the parabola, a perfectly horizontal tangent line. And when that happens, horizontal lines have slopes of 0. Now, what I'd like to do is plot my slopes. I want to plot -3, I want to plot 0, and I want to plot +3. So let me switch colors again because I'm about to sketch the derivative now. Well, my 0 slope happens right here when x is about -1. So I'm going to plot -1, 0. My slope of -3 is maybe over here at -4 or -3.5. So maybe I'll just say -3.5, and I'm going to plot an output of -3. 1, 2, 3 down here. Again, I'm plotting the slopes as I'm sketching them out. And then finally, +3, so maybe at, maybe right about at 3, or sorry, at x equals 2, I'll come up here and put a slope marking there of +3. And it's just a very rough sketch of where those rates of change might be plotted. So now, though, look at this. You have a linear relationship between those slopes. So connect the dots. And let's label that, let's try again here, our derivative, f prime of x. The next picture down here is even more complex. We have what looks like some sort of cubic function, x to the power of 3. So let's analyze the slopes here. And I have a note that says to find where the slope is equal to 0 first. And it's often going to be the easiest thing to find. So I see a 0 slope right there, and I see a 0 slope over here. So go ahead and mark on the picture where those slopes of 0 occur, because that means I can go right down to the x-axis, and right below it or right above it, just put a point for the derivative. Now let's look at what else I have here. I've got a pretty positive slope increasing over here. If I draw a little tangent line sketch, it looks like I'm going to be going maybe up 1, 2, 3, maybe up 4 and over 1. So a slope of about 4, a very rough estimate. There's nothing really mechanically perfect about this. And let's see here. What if I go over here to the far right-hand side and again, look for maybe some slope estimations. Maybe this is a slope of, let's see here. So 1, 2, 3, up 3 and over 1, maybe a slope of about 3 or maybe 3.5 right over there. But then notice in between the two horizontal slopes, I have a negative, a decreasing slope. And that appears to be, let's see here, maybe -1. So I want to plot that down here at -1. Here I said it was up to 4, so 1, 2, 3, and 4, maybe off my grid a little bit. So something like that. And here we said 3, maybe something like that. And as we can see, when we switch colors back to blue, if I connect those points, I'm starting to see something that looks almost like a parabola. Let's label that our sketch of f prime of x. Again, very, very rough sketches and estimation. There's nothing really perfect about this, but I'm getting an idea, I'm getting a sense on what the values are of the derivative for these functions. Now, one more over here. Here, this looks like an upside down absolute value graph. The good news is absolute value graphs are really piecewise linear functions. So I can count exactly up, let's see here, up 2 and over 1. So a slope of +2 on the left. And this appears to be a slope of down 2 and over 1, so a slope of -2 on the right-hand side. So let's graph this. Switch colors to blue. And let's go up here to +2. Now be careful with that cusp, that sharp corner. I'm going to put an open circle here, and I'll show you why in a minute. And then the slope of -2 all through there. Oops. Let's make sure that we stay within the domain of the function. This function is only defined, it looks like, from -4 to +2. So let's not assume that we know what's happening on the outside of those boundaries. Anyway, here's my f prime of x sketch, once again in blue. And notice that I have a corner right here on my absolute value graph, a cusp, or sometimes it's called a corner. At cusps, the derivative does not exist. So there is no value for f prime here. If you think about it in terms of limits, the limit of the rate of change of my function, of my slope essentially here, is +2, but on the right side, the limit is -2. Those two limits don't match, so the limit overall, at the point, in this case, it looks like x equals -1, does not exist. There is no derivative value, there is no slope, there is no tangent line that I can draw and have a value. So f prime does not exist at cusps and corners, so make sure we leave that sketch undefined. Something like that would be okay. So that's how you make graphical sketches and approximations of the derivative. You can try the remaining 2 examples here, a little bit more challenging than the first 4 that we did, but you can look for the 0 slopes first and then kind of find your rates of change around the function and then plot them to connect what should be a pretty accurate sketch of what we believe the f prime derivative function will be.